The war had taught the British Army a bitter lesson in the autumn of 1942. Armor was no longer merely a suit of protection, but an evolving system of mechanical sophistication that demanded respect, study, and above all, understanding. When General Montgomery's 8th Army clashed with Rommel's Panzer Army Africa in the deserts of North Africa, something profound changed in British military thinking. It was not just about defeating an enemy, it was about comprehending the very machinery through which that enemy fought, dissecting it, learning its secrets, and using that knowledge as a weapon of its own. The engineers and metallurgists at the Ordnance Board in London began to grasp what would become an obsession: to know how the Germans built their tanks, how they solved problems that British designers were still wrestling with, and crucially, what weaknesses lay hidden beneath the armor plate of their most formidable creation, the Panzerkampfwagen VI Ausführung E, known to the Allies simply as the Tiger. The machinery of war, it seemed, was a conversation written in steel and innovation. The German reply to British armored advances had come in the form of this revolutionary tank, first encountered in Tunisia in 1942 and immediately recognized as something that demanded urgent technical scrutiny. While British and American commanders assessed its combat performance through the lens of battlefield tactics, another group of men, quieter, more methodical, armed with measuring instruments and chemical analysis equipment rather than rifles and intelligence reports, was preparing to engage in a different kind of interrogation. They would dismantle the German war machine piece by piece, not in anger, but with the cold precision of scientific inquiry. These were the men of the Technical Intelligence Services, supported by the Defense Research Policy Committee, and the various facilities scattered across Britain where captured enemy weapons were methodically reverse-engineered, photographed, sketched, and analyzed. By 1943, after the end of the North African campaign and the capture of several German tanks, these facilities had begun to accumulate specimens that would provide an unprecedented window into German engineering philosophy. One particular Tiger, captured largely intact during the withdrawal from Tunisia in May 1943, would become the subject of intense investigation. This tank, bearing the tactical number of a company within the 501st Heavy Tank Battalion, had been abandoned by its crew when engine trouble rendered it immobile during a withdrawal near Sfax. British recovery teams, moving quickly through the tactical zone, had secured the vehicle and eventually transported it back to Britain. The journey itself was remarkable. The tank was disassembled, its major components carefully packed, and transported first by ship through the Mediterranean and around the Cape of Good Hope to the United Kingdom, arriving at the Farnborough Aircraft and Armaments Experimental Establishment, and subsequently at other testing facilities. It was here that the real work would begin, the microscopic examination that would reveal not just how the Tiger was built, but why it was built the way it was, and most importantly, what compromises and material challenges the Germans had been forced to accept in their drive to create an armored fighting vehicle of unprecedented capability. The transmission represented one of the most crucial systems in any tank design. It was the mechanical bridge between the engine's raw power and the tracks that would propel the machine across terrain, up hills, through mud, and across rivers. The transmission had to transmit tremendous force.
While maintaining precision in its gearing ratios, it had to withstand enormous stress during engagement, and it had to operate reliably in conditions ranging from the frozen steppes of Russia to the blistering deserts of North Africa. In the German Tiger, this system was particularly complex, featuring a Maybach Olvar semi-automatic transmission connected to the powerful Maybach HL230P45 engine that produced 700 horsepower.
The transmission was not merely a collection of gears. It was a sophisticated mechanism incorporating fluid couplings, hydraulic controls, and meticulously engineered gear trains that had been designed to provide the Tiger with superior mobility and firepower coordination that few other tanks of the era possessed. Yet it was precisely this sophistication that would prove, under the scrutinizing examination of British engineers, to contain the seeds of fundamental weakness. The examination began methodically, almost ritualistically. Teams of engineers and technicians at the Technical Intelligence Base near Chertsey began the slow process of documentation. Every angle was photographed, every dimension recorded, every material identified. The gearbox was extracted from the transmission housing with painstaking care, photographed in situ, and then removed for detailed analysis. The gears themselves, these intricate mechanical components that had seen combat service, that had transmitted the force of the German war machine across North African sand, and European mud, were subjected to scrutiny that would have been almost unimaginable in peacetime, but which wartime necessity had rendered essential. Under magnifying glasses and increasingly sophisticated instruments, examining engineers noted the precise geometry of each tooth, the surface finishes, the material composition. Samples were taken, chemical analysis was performed, and the results began to reveal something startling. The metallurgical foundation upon which the German transmission rested was not what anyone had expected. The problem became increasingly apparent as the analysis deepened. The British metallurgists discovered that many of the critical gears in the Tiger transmission, particularly the heavily loaded gears that bore the greatest stress during operation, were made from a steel that, while adequate in basic composition, had been subjected to a heat treatment process that had produced unexpected brittleness at certain stress points. This was not a matter of inferior material as such, but rather a more subtle failing, a compromise, born of necessity and the particular demands that German industry was facing as war production reached fever pitch. Germany, by 1943, was engaged in intensive production of multiple tank types, and raw material constraints had begun to force engineering decisions that would not have been made in peacetime. Certain alloying elements that would have produced superior mechanical properties were becoming increasingly scarce or difficult to allocate. The vanadium and molybdenum that might have enhanced the strength and wear resistance of these critical transmission components were being prioritized for other applications, or were simply unavailable due to the interruptions in supply lines and the strains on the German war economy. The heat treatment regime itself told a story. The German engineers had attempted to compensate for the compromised material composition through careful control of the heat treatment process, tempering and quenching the gears to achieve a balance between hardness and toughness. But the process had its limits. Under extreme loads, particularly the sudden shock loads that would occur when a tank was navigating broken terrain or engaging in the violent maneuvers of combat driving, these gears would exhibit a tendency toward brittle failure. The British found evidence of microcracking in some of the teeth, patterns of wear that suggested stress concentration at certain points, and laboratory testing confirmed the suspicion. Gears from a Tiger transmission failed under stress conditions far sooner than comparable British transmission components would have failed. What was particularly remarkable was that this failing had not resulted from any fundamental conceptual error in the German design. The transmission itself, as a system, was actually quite well conceived. The problem lay not in the engineering of the design, but in the material compromises that the Germans had been forced to accept, and in the limits of what even excellent engineering could accomplish when working with material that was, fundamentally, not quite as well suited to the application as one might desire. This discovery led the British investigations in new directions. Interrogation of captured German engineers and technical personnel, when combined with this material evidence, began to paint a picture of the systemic pressures that were shaping German weapon production. The engineers learned that the Tiger had gone through a relatively rapid design cycle, driven by the urgent need to counter British and Soviet advances in armor and firepower. The Daimler-Benz design bureaus had worked at an intense pace, and while the basic engineering was sound, the time available for material testing and refinement had been compressed. Furthermore, the allocation of raw materials within the German economy had become increasingly subject to competing demands. Panzer production was only one demand upon German metallurgical capacity. Aircraft construction demanded ever-increasing quantities of aluminum and special alloys. Ball bearing production competed for resources, and the military, at all levels, was making demands that exceeded the available supply. The result was a constant series of compromises, a technical struggle to maintain performance while accepting material limitations that would, in an ideal world, have been unacceptable. The transmission investigation also illuminated something deeper about the entire Tiger design philosophy. German engineers had compensated for material limitations and production realities through sheer sophistication of design. Every component was engineered to extract maximum performance from the materials available. Every system was refined to achieve remarkable capabilities within the constraints imposed by the available raw materials, the state of German metallurgical technology, and the demands of rapid production. The Tiger, examined in its totality, represented a triumph of engineering problem-solving under extreme constraints. It was, in a sense, a monument to what could be achieved when brilliant engineers were forced to operate at the absolute edge of material science and manufacturing capability. Yet it was also, when examined in minute detail by British metallurgists working with unlimited time and freedom to think, a revelation of just how narrow the margin between success and failure had become for German war production. The implications of these discoveries rippled through the British military technical establishment. Officers and engineers who had feared the Tiger, who had studied its combat performance and noted its apparent superiority in firepower and mobility, could now see the hidden fragileness within it. The Tiger was not, as some had suspected, a perfect weapon forged by German metallurgical supremacy. Rather, it was an increasingly desperate attempt by German industry to maintain technical superiority despite mounting material pressures and the strains of a war economy operating at maximum capacity. The transmission study became part of a broader British understanding that German weapon production was beginning to show signs of strain, that the Germans were fighting not just against external enemies, but against the mounting pressure of resource constraints and the law of diminishing returns in production. The Tiger represented the peak of what German industry could achieve given its material position in 1943. It also represented the point beyond which further improvement would become extremely difficult, if not impossible, without fundamental changes in the availability of raw materials and the overall strategic situation. The British examined and documented the transmission mechanisms with the precision that only wartime necessity and unlimited access to enemy equipment could enable. They produced detailed technical drawings, conducted stress tests on recovered components, analyzed failures, and compared German transmission performance to British designs. Every finding was carefully catalogued, recorded in technical reports that circulated among the military and engineering establishment, and used to inform the ongoing design of British tanks, particularly the Cromwell, which was already moving toward production, and the future designs that would eventually lead to the Centurion. The transmission of the Tiger, in its compromised but sophisticated complexity, became a kind of Rosetta Stone for understanding the current state of German technical capability and the hidden stresses within German war production. Yet the story of the Tiger transmission was only one chapter in a much larger narrative of technical intelligence gathering. The British Army, by the middle years of the war, had established sophisticated systems for capturing, recovering, transporting, and analyzing enemy weapons. Special recovery teams operated behind the front lines or in secured areas, seeking out damaged or abandoned German tanks and recovering them for technical analysis. These vehicles were then transported through supply lines that had become increasingly long and complex as the war progressed. One remarkable capture had occurred in 1943, when a nearly intact Tiger tank was recovered near the town of Gela in Sicily during Operation Husky, the invasion of Sicily in July 1943. This tank had been abandoned by its crew and subsequently recovered by British forces. Its journey to Britain and into the technical examination facilities represented an astonishing feat of logistics and organization during active combat operations. The recovery operations themselves were often conducted under conditions of considerable danger and difficulty. Tanks were heavy, mechanical behemoths, often weighing 60 tons or more, that could not simply be driven to a port and loaded aboard a ship. Instead, they had to be partially disassembled in the field, transported on specially reinforced railway cars, and reassembled for the sea journey. If a particularly valuable specimen like a Tiger could not be moved completely intact, it would be methodically disassembled, each major component carefully crated and recorded, and then transported separately. The organization required for such operations was immense. Recovery teams had to be equipped with the necessary heavy equipment, trained in the procedures for safely dismantling powerful military vehicles, coordinated with the tactical units that might be operating in the area, and supplied with the secure communications necessary to coordinate their activities. The maritime journey itself represented another series of challenges and adventures. Tigers were transported across the Mediterranean, around Africa, and across the Atlantic, aboard merchant vessels that had been equipped with special fittings and secured holds. The submarine threat, which was still very real in 1943 despite the increasing effectiveness of Allied anti-submarine warfare, meant that these journeys were conducted in constant awareness of danger. German submarines, operating from bases in occupied France and Denmark, still prowled the Atlantic in search of merchant shipping. The Type XXI and Type XXI U-boats of the Kriegsmarine were formidable adversaries, and several convoys carrying military equipment and strategic raw materials had been intercepted and sunk.
The fact that no major convoy carrying captured German tanks appears to have been attacked and sunk during its journey is something of a fortune, whether due to luck, to the secrecy of the routing, or to the increasingly effective British convoy protection measures is not entirely clear from available records. Nevertheless, the fact that these specimens were successfully transported across thousands of miles of ocean and delivered to British facilities represented an achievement that deserves recognition alongside the more dramatic naval actions of the war.
Once the tanks arrived in Britain, they entered a different kind of technical battlefield. The examination facilities at Farnborough, Chertsey, and other locations represented the cutting edge of British military technical intelligence. These facilities were staffed with some of the most capable engineers, metallurgists, and technical specialists that Britain could muster. Many of these men were academics drawn from universities and research institutions. Others were skilled technicians with years of practical experience in engineering and manufacturing. They had access to sophisticated testing equipment, chemical analysis laboratories, and the freedom to take apart and examine equipment with the kind of thoroughness that only a research environment, supported by military necessity and unlimited access to enemy specimens, could permit. The examination of German equipment became, in many ways, a gigantic laboratory in comparative engineering. Every tank, every aircraft engine, every weapon system that fell into British hands was carefully studied, dissected, tested, and its design principles catalogued and analyzed. The Tiger transmission study was particularly important because the transmission represented one of the most technically demanding systems in a tank. The design had to balance multiple competing requirements. It had to transmit enormous power from the engine to the tracks. It had to allow the driver to select different gears for different conditions. It had to include some form of automatic or semi-automatic engagement system to reduce driver fatigue and maintain smooth operation. And it had to be reasonably maintainable in field conditions. The Maybach-Olvar transmission installed in the Tiger was a masterpiece of German engineering in many respects. It featured a sophisticated system of hydraulic controls that would partially engage gears before full mechanical engagement, reducing shock loads and allowing smoother gear changes. The design showed careful thought and sophisticated engineering. Yet the material limitations that constrained its performance revealed something important about the state of the German war effort. The examination of the Tiger transmission and other German components began to fill in a picture of German technical development that was, in many ways, at odds with British expectations. The popular understanding in Britain held that German engineering was fundamentally superior, that German factories represented the cutting edge of industrial capability,
and that German designers were essentially invincible when it came to military technology.
The careful technical analysis conducted by British engineers began to modify this understanding. German engineering was indeed often brilliant and innovative, but it was operating under constraints that did not always allow for the kind of optimization that British designers could achieve when they had access to sufficient materials and adequate time for development. The German approach was often to design around the constraints, to achieve superior performance through sophistication and ingenuity, rather than through material superiority. This made German weapons formidable and often superior in specific respects, but it also created vulnerabilities and limitations that British designers, working with different resource constraints, might not have encountered. This insight was particularly valuable because it suggested that the war might not be decided simply by technical merit, but by the ability of each side to maintain production and material supply. The Germans, by 1943, were showing signs of strain in their ability to sustain the production of sophisticated weapons that required precise material composition and careful manufacturing processes. British production, by contrast, was still ramping up. The loss of production facilities to German bombing had been largely compensated for by decentralization and new construction, and raw material supplies were being secured through the development of new sources and the maintenance of the sea lanes through which these materials could be imported. The Tiger tank, far from being the invincible weapon that British soldiers sometimes feared, was actually a harbinger of German technical decline, not because it was poorly designed, but because it represented the absolute limit of what German industry could achieve with the resources available to it. The transmission study contributed to a broader British assessment that concluded that German technical development had essentially reached its peak by 1943, and that German industry would face increasing difficulties in maintaining production at the required levels while simultaneously producing new designs that could match or exceed Allied advances. The Tiger would remain a formidable weapon throughout the war, and later variants with improved armor and firepower would present even greater challenges to Allied forces. Yet the fundamental insight that German technical capability was operating at the edge of industrial capacity and material availability proved to be correct. German production did face increasing constraints, and by 1944-1945, German war production had begun to decline as the strategic situation deteriorated and Allied bombing campaigns became increasingly effective. The investigation into the Tiger transmission gears thus became more than a simple technical examination of a specific component.
It became a window into the broader technical-industrial situation facing Nazi Germany, a revelation of the hidden pressures and constraints that were shaping German weapon development, and ultimately, an important contribution to British understanding of the nature of the conflict they were engaged in.
The examination facilities at Farnborough and elsewhere became increasingly valuable sources of strategic insight, as the continuous stream of captured German equipment provided a real-time window into the evolving state of German technology and industrial capacity. The broader implications of the transmission study extended beyond the immediate questions of tank performance and design. The British realized that they were engaged not simply in a military conflict but in a competition of industrial systems and material availability. The discovery of material compromises in the Tiger transmission suggested that German industry was already beginning to show signs of strain, that the vaunted German engineering establishment was increasingly forced to accept solutions that represented compromises with ideal material specifications and manufacturing processes. This had profound implications for British strategy and resource allocation. It suggested that sustained British production, even if individual British weapons were not always superior to their German counterparts, might ultimately prove decisive. A tank that was somewhat inferior but which could be produced in greater numbers and with more predictable performance characteristics might prove more valuable than a superior tank whose production was constrained by material limitations and whose performance was affected by subtle material compromises. These insights contributed to the thinking that produced the British tank development programs of the latter half of the war and the immediate post-war period. The recognition that German engineering was operating at the edge of material constraint led British designers to place perhaps greater emphasis on design sophistication and material optimization than they might otherwise have done. The study of captured German equipment provided a kind of technical education that accelerated British understanding of advanced engineering practices
and helped inform the design of post-war British tanks that would, in some respects, represent the world's most advanced tank designs of their era.
The story of the Tiger transmission examination represents one of the more understated but nevertheless significant episodes in the technical history of World War II. While dramatic tank battles and air combats captured the imagination of the public and featured prominently in historical narratives, the patient work of examining, analyzing, and understanding captured enemy equipment represented an equally important contribution to the ultimate victory of the Allied powers. The teams of engineers, metallurgists, and technical specialists who worked at the examination facilities were not in the headlines, did not feature in combat reports, and in many cases, their contributions to the war effort were classified and remained obscure even after the war ended. Yet their work provided essential information that shaped British military thinking, informed weapons development, and contributed to a realistic assessment of the nature and prospects of the conflict. The technical intelligence gathered from the examination of German tanks and other equipment represented, in many ways, an early example of what would later be called competitive intelligence analysis, a systematic effort to understand the technical capabilities, limitations, and direction of development of a rival power through careful study of their actual products. The techniques developed during World War II for recovering, transporting, and analyzing captured equipment would become formalized in post-war years and would continue to be refined and developed throughout the Cold War.
As successive generations of intelligence analysts sought to understand the military capabilities and intentions of potential adversaries through careful technical examination and analysis.
The story of the Tiger transmission gears is thus, in its own way, a microcosm of the larger technical history of World War II. It represents the intersection of brilliant engineering, industrial capacity, material constraints, strategic necessity, and the emergence of systematic technical intelligence gathering as a crucial component of military analysis and strategic planning. The gears themselves, those intricately shaped pieces of steel that had rotated at high speeds while transmitting hundreds of horsepower through the transmission of a German tank, became something more than mere mechanical components. They became artifacts of a moment in history when German technical brilliance had reached its peak and simultaneously begun to show signs of strain under the mounting pressures of a war economy, operating at absolute maximum capacity. The examination of these gears by British metallurgists thus yielded insights that extended far beyond the technical specifics of transmission design. It provided a window into the broader technical and industrial situation that would determine, in substantial measure, the ultimate outcome of the war itself. The discoveries made by British engineers studying the Tiger transmission
would ultimately contribute to a more nuanced and sophisticated understanding of German technical capability and industrial capacity that would shape British military planning and resource allocation for the remainder of the war and the immediate post-war period.
The recognition that German engineering, while often brilliant and innovative, was operating under material and industrial constraints that differed from those facing British industry, led to different strategic and technical conclusions about how to allocate resources and where to focus development efforts.
The modest Tiger transmission, examined with such meticulous care and analyzed with such technical sophistication, thus became an unsung contributor to Allied victory, not through any direct military application, but through the insights it provided into the nature and limits of German technical and industrial capability in the crucial year of 1943, when the outcome of the war was still very much in doubt, and every scrap of technical information about the enemy could potentially influence the decisions that would ultimately prove to be decisive.
The examination of captured Tiger tanks and their components continued throughout the war and into the post-war period. As additional specimens fell into Allied hands, particularly after the D-Day invasion,
when German equipment left behind in retreat could be systematically collected, the database of technical knowledge about German tank design and manufacture continued to grow. The transmission study, initiated in 1943, thus represented the beginning of a systematic program of technical analysis that would continue expanding and deepening as the war progressed.
The insights derived from the study of the Tiger transmission would be refined, expanded, and integrated with information from other sources. Interrogation of German engineers, analysis of German technical documents, examination of other tank types and components to create an increasingly comprehensive picture of German technical and industrial capability. This accumulated knowledge would prove invaluable, not only during the final stages of the war, but also in the immediate post-war period, when the British military and intelligence services had to assess the technical situation in occupied Germany and determine what knowledge and capabilities should be preserved, protected, or shared with Allied partners as the post-war world began to take shape.